Same? I don't know. Okay, guys, good morning to everybody. Questions about lab this week? Questions about previous material? Okay, let's look at, just make sure, ring-forming reactions. Let's see if we finished up everything under A. Ring-forming reactions, we looked at two types. It says intramolecular reactions. It's actually not strictly correct. We did both inter and intramolecular reactions. Roman numeral 5. But this here was a, no, I reckon it would be correct. Yeah. This is an intramolecular reaction. Internal. Inter would be two different molecules, like interstate goes between two different states. One molecule, internal, will be intramolecular reaction to give this ring. But also in the THC example, this is another intramolecular reaction to make this ring here, the 6-membered ring here with the 1 oxygen in it. So please look at that example, and I will send out a mechanism for that reaction. But now we're ready to start B, electrophilic reactions without a carbocation. And these reactions are all shown down here in the midsection here. A model alkene, and the first reaction we'll look at is reacting with X2, which is halogen 2, elemental halogen like Br2, Cl2, not HX, but X2. And we're going to get a trans dihalide, but we'll start there and we'll come around this way and we'll look at these reactions. So on the outline, the first is Roman numeral 1, anti or trans addition of halogens to give what type of product? Yes, a bisphenol dihalide. So let's look at this reaction here. If we take an alkene, they will react with like Cl2 or Br2. Those are the most common. We'll mention other halogens like I2 a little bit later. And the product here is we're adding each halogen across the double bond. So each carbon gets a halogen. All right, each carbon now has a halogen. That's pretty simple because we don't even have to say which carbon gets the H, which carbon gets the halogen, because it's the same thing. They both get the same thing. So there's really no decision there in terms of the outcome. Major thing here, though, is the mechanism for this reaction. Also the stereochemistry that's built into it. By the way, stereochemistry. Let's go back over here a little bit. Okay, guys, a number of you coming in late. Cannot come in late. All right? If you want to participate, involves showing up. More people coming in late. Let's look at stereochemistry here. Typical hydration. We're doing hydration in lab this week. Okay? Product. OH is going to be on the left carbon or right?
Left.
You have the left carbon, because that's the same place the carbocation would be. Okay, product here would be boom, boom. Boom, boom, boom. Boom. There's your product. You should be thinking mechanistically how you get to that product. Okay, every step. Be able to predict that product. I can just do it in my head. You guys should be working it out most likely. Okay. Ultimately, you get to the point where you see what's going on and you can predict it in your head. What about stereochemistry of that product though? As we move forward, we'll learn that this carbon here is chiral. Okay? Stereochemistry is coming soon. And this product is going to be, I'll show here, boom, 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 boom. We can get the OH forward, but we can also have the OH back. And both are formed. And it's actually a 50-50 mix. And we will call that racemic later on. Why do we get both formed? It comes from the cation. Boom, 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 boom. The first intermediate is the carbocation, right? And water attacks the carbocation. All right? And this is the type of thinking we're going to need to be doing more as we go forward, is how does it attack, what's the stereochemistry, the projections, the orientation of the bonds? What's the hybridization of the carbocation? And thus geometry. sp2, trigonal planar. Okay, it's trigonal planar, flat on the board. All right. When the water attacks it, it's attacking a flat plane. All right, just like a piece of paper. Here's a carbocation. It's trigonal planar, like a piece of paper. All right. Make a bond to it. All right. There you go. You made a bond. Your bond, is it pointing forward or backwards? Forward meaning towards the class, pointing that way, which is towards the classroom. Your bond is like that, because it came from you, unless you threw a boomerang and came from around here. Okay? All right? But guess what? In molecule land, this is floating around. Okay? If you tack it over here, the bond's this way. You tack it over here, well, the bond's that way. You have a 50-50 chance. All right? Here we go. Water. You attack it this way, bond's that way. But you attack it this way, bond's that way. That's why you get both, because you can either attack from the front. If you attack from the front, which one are you going to get? This one. The new bond is from the front, pointing this way. Or you can attack it from the back. If you attack from the back, you get the other. You got a 50-50 chance in molecule land. That's why you get a 50-50 mix. Because you're attacking a trigonal planar carbocation. All right? So that's important here, and you actually, 50-50, we call this racemic. We'll see more of that. But that was the idea of stereochemistry there. Anybody get a product of this one down here? I have a product? What do you have? Can you describe it?
Is it ether?
Yes, it's an ether. Is it that ether there?
Yeah.
Yeah, it's a 6-membered ring. Got the methyl and you got the O-ethyl here. This was an example of using an alcohol instead of water. If you use an alcohol, The R group on your alcohol is just going to be on your oxygen. You'll lose the H in your mechanism, but you don't lose the R group. Since the R group is there, that's actually an ether. Okay? So that was Roman numeral 3. But Roman numeral 3 is really no different than Roman numeral 2. It's just you got an R group, and since you got an R group, it's called an ether. Mechanistically, yeah. Attack H+. The H+ comes from the HF. HF is a strong enough acid to do this. It's a dry acid. Why do you want to use a dry acid? What if we used an aqueous acid? Use an aqueous acid, there'd be water here. And water could attack the cation, and you would get an alcohol. You don't want water to attack. If you want ethanol to attack, you'd rather use a dry acid. Ethanol can attack, all right, and then when you lose the H from the oxygen, you have an ether. Okay, so those are a couple of miscellaneous things before we move on. Back over here. So we can add halogen 2 across the pi bond to get a dihalide. It will be vicinal. What does vicinal mean? You make sure you know what vicinal means. Let's look at mechanism. Pi bond is a source of electrons. The chlorine looks like it's nonpolar. You've got two equivalent atoms. But actually, your halogens are easily polarized. Any compound is polarizable. When we talk about London forces or van der Waals, that's polarization of molecules by them rubbing into each other. Okay? Well, molecules are always rubbing into each other. This can be rubbing into another chlorine molecule. It can be rubbing into this. It can be rubbing into oxygen, because usually oxygen's around when you're doing reactions. All this rubbing in leads to polarization. Your halogens are very easily polarized. They're schizophrenic. Even though it's officially nonpolar, it can become polarized, and we can maybe just say, okay, somehow through perturbation of electrons, it became polarized. Very easy for halogens. And so we can show this and this. These electrons can attack the Cl and kick the other one off. That's a lot like attacking the H and kicking the chlorine off. We attack the H, this is a permanent dipole. Attack the H, kick the chlorine off, attack the chlorine, kick the chlorine off. Where are we going to leave cation here, left or right? Cation on the left, correct? Okay. So electrons attack chlorine, this one gets kicked off, leaving cation here. So we made a new bond to chlorine. From here, we can go two different ways. First, let's look at the way that's incorrect. The chlorine that got kicked off became chloride when it took on a fourth lone pair. The chloride could come back and bond to the carbocation. We've seen that before. If that happened, you would get the product, right? Yes, you would. The problem is that's not the mechanism. Not the mechanism, and we'll explain how we know that in a little bit. The mechanism that's known is shown this way. So not the A arrow, but instead, and this actually makes sense, the electrons from the chlorine that was added is what comes back in bonds. Because this guy has electrons that can come in here. And it actually makes sense. Which is going to be more likely to come in here and bond? The one that's right next door because it's already bonded and it's just 2 atoms away, or the one that's floating maybe a little bit further away. This one's real close. It's actually the one that comes in. And if this comes in and makes bond, what do you get? You actually get this 3-membered ring because the chlorine that was bonded over here comes in here, and I call it back bonds. No book is going to call it that, but I use this terminology. It's kind of used in advanced chemistry some places. It back bonds. This one back bonds instead of this one coming in. That's faster because it's closer. Just like right here. Let's slap hands. Give me a high five, okay? Now I'm going to brace you. Now I'm real close here because I'm bonded here. Go ahead. Beat you, sorry. You didn't even have time to move. Boom, I'm right there. Real easy, right? Real easy for this guy to come here. Back bonding so much faster. We get this. This is a 3-membered ring. Yes, it's strained. By the way, the chlorine is now positive. Because if you can do a charge, it's positive. The lone pair is now a bonding pair. This is called a chloronium ion. 3-membered ring, positive chlorine. We'll also see bromonium ions, analogous bromine. From here, now that external chloride comes in, and it attacks the same carbon as the cation, but it attacks a carbon that's back bonded. And these electrons come in, just like we got here. These electrons come in, attack this carbon, and kick these electrons back off. All right, already had the arrows there. So this chloride does not attack a free carbocation. It attacks a carbon and kicks a leaving group off. Now you should all be familiar with these 2 attacks. You can either attack a carbocation, and that's what we've done before in all of our reactions. But here, we're attacking a carbon and kicking off a leaving group. Okay? And so this was all covered over here on the green sheet. Two mechanisms for making nucleophiles of carbon bonds, right? Okay. Attacking carbocation. We've done that. Why do you get 2 outcomes? Well, we explained that at the beginning, right? Okay, it's all right there. The other way is to attack a carbon and kick off a leaving group. Right? This actually gives a certain outcome in terms of stereochemistry. But it was all right here, yeah? So at this point, we're looking at that second mechanism type. Chlorine comes in, kicks off the leaving group. All right? It was a leaving group. A leaving group is something that leaves. It's leaving this carbon, being kicked off by the nucleophile. I'm the only one that you'll see call it LG. LG means leaving group. Okay? So, what is this? What does all this give? Well, this gives your final product. Because chlorine is now bonded to this carbon. And when this gets kicked off, it now has its 3 lone pairs back, and it's still bonded to that carbon. So 3 lone pairs, right? 3 lone pairs. This is also called, when you attack a carbon and kick off a leaving group, that's always done backside. And so it's often called backside attack. Backside attack. How does that compare to what we did before? Here's a carbocation. Planar. I can pull it like that, I can pull it like that. Which side are you going to attack the carbocation? Why over here?
The closer side of the ring.
Is what?
The closer side of the ring.
Well, that makes sense, closer side to where you are. But let's consider that there's a million of you around here surrounding this. So which side are you going to attack? Only one side or both? You can attack either. You attack cations either side. Right? For example, if I'm standing right here, you attack over here, but you're going to attack over here. Yes. Closer, closer. But either side. Whenever you attack a carbon to kick something off, you only attack from one side, and it is backside. For example, here we go. What if you're going to kick off this pin? Which side would you attack from? What? Okay, and it's called backside. So attack backside. Boom. You just knocked me off. You came in backside, opposite the leaving group. That's called backside. Okay? So what's going on here? That's what's explained on that green page. Both two types of mechanisms. You can learn the two types of mechanisms, then you can do anything. Because it's all the same. Test 3, backside attack. Okay? Here's our chance to understand fundamentally the mechanism types. What we don't want to do is just memorize these connections and be able to repeat it on the test, because that does nothing for you. Understand the terminology, the chemistry, the mechanisms. Okay. How many intermediates in this mechanism? There's actually only one. This is the only intermediate. Then what is this? By the way, very importantly, we're under Roman numeral or letter or what? B. What does B say? These are reactions without a what?
Carbocation intermediate.
Without a carbocation intermediate. Then what is this? Looks like a carbocation intermediate to me. So what's going on here? It says it should not have a carbocation intermediate. That's because it does not. This is not actually formed. NAF. Not actually formed. Okay? There's only one intermediate in this mechanism, and it's the chloronium ion. Only intermediate. Then why am I showing this? I show this because I think it's helpful for understanding what's going on. Because if I had went directly to this, usually you guys are like, hold on, what happened here? I'm trying to help you see how we got there. So I show this. But it's not actually formed. Because the first two steps, these two steps, which look like separate steps in my mechanism, these happen at the same exact time. And when things happen at the same exact time, we call it concerted. This is all concerted. And the first intermediate is this. This is only me doing it on the board. And if you show this on an exam, if you don't put NAF, then you're going to be wrong. Because now you're welcome to not even show this, because some books do not. Go directly from here to here. But to go from directly to there, you have to have another arrow. You have to then come back here. And to me, that's too many arrows. It's like, what's going on here? I choose to show this, but it's not actually formed. It helps us get to where the first thing that's formed, okay? That is, as soon as the pi bond, okay? Why don't we do some more theater here? Can you guys be chlorine? So you're all bonded together, okay? A little schizophrenic. Y'all bumped into oxygen and became polarized. I attack the chlorine. Ooh, a positive chlorine. I go bond to you. The electron, you take the electrons. You would like to be minus anyway, right? You're chlorine. So you pull the electrons because this chlorine is now bonded, leaving this as a cation. Okay? We got rid of you. You have a lone pair. What's going to happen next? This is a cation. you're going to back bond to the cation. So back bond, one more hand. And we make a 3-membered ring. Okay? Back bond and make a 3-membered ring. But here it is. Instead of it all happening one at a time, boom, cation, and then you back bond. Let's do it at the same time. Okay? As soon as I come your way, you come my way. Boom. And there's your first intermediate. Both happen at the same time. As soon as you attack the chlorine, this is actually back bonding. Same time, inserted, and this is not actually formed. I think it's helpful to show it anyway, though. This then attacks the carbon. Which carbon does it attack? Because you could actually attack either. We could attack here and kick this chlorine off. You actually attack the same carbon as where there was a cation. So that's another reason I think it's decent to show this. We're going to attack there, but it comes from attacking the chloronium ion. Let's look at why do we attack here and not here. This is shown over here on the right. This is a strained 3-membered ring. Even though the chlorine is bonded, it's still very electronegative, so it pulls on those electrons. It can pull on these electrons and weaken this bond, and that would lead to this being only partial plus, and that would be partial plus. Or it could pull on this carbon and weaken that bond. This meaning like sort of a partial bond. Okay? Which is a better scenario? The answer is this one. Because it all depends on the carbon. Which carbon is more likely to be partial plus? This one, because it's more substituted. That's the same carbon that would be more likely to be just full plus. Back over here, would you rather make carbocation on the left or right? On the left, because it's more substituted. Well, where would you rather have more of a partial plus? Left or right? It's the same answer. Right here. And so really, when this guy is looking around and is like, okay, am I going to attack here or here? It attacks here. And these electrons just get completely kicked off. So you attack this carbon, but again, it's the same place where you make carbocation. Okay, in terms of predicting product with no stereochemistry, it's a pretty darn easy reaction because boom, boom, boom. Here we go. We add a bromine to each carbon, right? Here you go. Whenever you react an alkene with Br2 or Cl2, you add a halogen to each carbon. It's actually one of the easiest reactions you'll ever do in terms of predicting the outcome. The more important thing here is the mechanism, but also the stereochemistry. And when we have stereochemistry, what is the stereochemical outcome? Let's look at this reaction. You can't have variations. This is called an interhalogen, two different halogens. Now here you do have a permanent dipole. Which halogen here is electrophilic? The iodine or the chlorine? Which halogen is electrophilic? You got a 50-50 chance. Which one? Chlorine? Not the chlorine. Try me. Iodine is more electrophilic, yes. You know what electrophilic means? Chlorine is more electronegative, which means it pulls more, right? Since it pulls more, which atom is partial positive? Right? Iodine's partial positive. Well, that means it's electronegative. I'm sorry, not electronegative. Electrophilic. Chlorine's electronegative. As a result, the iodine is electrophilic. Electrophilic means it likes electrons. The iodine is going to like electrons more because electrons are negative. The positive halogen is going to like the negative electrons more. It's electrophilic because the chlorine is electronegative. I mean, the chlorine is not going to like electrons because it's already got a partial negative charge. It's going to actually repel electrons. Okay? The iodine, so the iodine is what these electrons attack the iodine. Where are we going to leave cation? Top or bottom? Bottom. So I pull away from here, attack the iodine, and kick off the chlorine. Okay, these electrons get kicked off, right? This leads to boom, 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 boom. So the N carbon is bonded to the iodine. 1, 2, 3, 4. Leaving this as a cation. Analogous to our previous reactions. But hold on. What's going to happen next here? The iodine does have 3 lone pairs. What's going to happen next? We also have a Cl minus. Which electrons are going to get here faster? These here are going to back bond. And what does that lead to? It leads to the iodine now bonded here, and it's got 2 lone pairs left. That's actually a positive charge. It would be called an iodonium ion. Now let's back up. Do you think the cation is actually formed? The answer is just like above. No. It's not actually formed. Because as soon as the pi bond attacks the iodine and kicks off the chlorine, what is the iodine doing? You see, most books will not show this. They'll show you an arrow coming here, and it will be coming in here. I'm just delaying that arrow until down here. Because I think if I combine it all, you guys will not see it. So I'm showing you something that's an intermediate that ain't really even an intermediate. That's just us on the board. It's not actually formed. I attack the iodine, but at the same exact time, you're bonding me. First intermediate, iodonium ion. There was never a carbocation. All right? That's just Stevens on the board. These 2 steps are concerted, same exact time. Here's your first intermediate. Then what's next? Then the chloride. See, this thing is strained. The iodine really doesn't want to bond. Why does it bond? Why does it even do this if it's strained? Because bonding is good. More bonds better. Even though it's strained, you do get an additional bond. But still the iodine is like, I don't want to be so strained. So this bond is a little weak. And you actually have partial plus here. And the chloride then comes in. How does it come in? It actually comes in backside and kicks off the iodine. And what do we end up with? Boom, boom, boom. Iodide on the end. And the chlorine is here. Right? And this is your product. At this point, let's not worry about any stereochemistry. Let's just get the atoms connected to the right atoms. Some of you will say, well, why didn't you draw the chlorine up if it came in from up? You could. That has free rotation. It doesn't matter. The important thing here is, if I'd asked you at the beginning, which halogen is going to end up on the N carbon? Well, the answer is iodine. But you need to, the way to know that is to know your reactivity, to know your mechanism, And then, there you go. You don't have to memorize it. If you know your mechanism, you can answer such questions. Okay. We'll look at the stereochemistry here later. Typically, these reactions are just with Cl2 and Br2. Your other halogen is not quite as good. First off, if you try to use fluorine, it tends to be so exothermic that it may explode. Okay? Reactions with fluorine tend to be dangerous. Right? We will not be using fluorine in the lab. Too exothermic, too... You'll see the video that I sent with the nitrogen triiodide. That's an example of a very exothermic reaction. We don't want to be doing that. It's because the CF bonds are very strong. If you get your calculator out, you'll see it's very exothermic. On the other hand, I2, those bonds are very weak. Carbon iodide bond is very weak, and so those reactions tend to be endothermic. Since they're endothermic, they don't happen that easily. They also tend to want to reverse. Turns out just the chlorine and bromine are the best here. We can use iodine sometimes, but it's often sort of mixed with something else. Maybe another nucleophile, or maybe an interhalogen like ICL. That works well. I2 tends to not work that well. Okay. Let's look closer at the stereochemistry here. You take this 6-membered ring cyclohexene, reacted with chlorine. Well, now we get a product with a chlorine on each carbon. That's pretty easy. Chlorine on each carbon. Chlorine is added across the double bond. But what about the stereochemistry? There are actually multiple stereoisomers that are possible, theoretically. For example, they could both end up being cis to each other. Well, there's actually only 2, and I've just repeated them. They can be cis to each other, or they can be trans to each other. And these are stereoisomers. They have the same connectivity. It's both 1,2-dichlorocyclohexane. 1,2-dichlorocyclohexane. They just have stereochemical descriptors that are different. Okay? Now just repeat the 2 over there. Something very important about this reaction. If you do this exact reaction, you only get trans. Okay? Trans only. Trans only. Plus an enantiomer. We'll learn about that in about a week or 2. The cis is not formed. Now, any mechanism you do must account for all the bonds being formed, but it must also account for the stereochemistry that's observed. So our mechanism must explain why is it trans only and why do you not get cis? Well, actually, our mechanism does explain that. By the way, just terminology. We only get one stereoisomer, so we say it's stereoselective. Okay? We'll learn more about this later on. Some of these things are just in the notes, so when you look back. Why do we only get trans? Well, let's go through the mechanism again. Pi bond attacks the chlorine, it gets kicked off. The other one gets kicked off. This leads to carbocation, maybe? Importantly, though, this carbon is now tetrahedral. So it now has 4 bonds. So the new chlorine is either going to be forward or back. I drew it forward. I could have drawn it back. You've got a 50-50 chance. Because if I'm the alkene, I could attack forward, and the new bond would be forward from the alkene. But maybe you're over here, and I could attack this way. And so the new bond would be back. I have 50-50 chance, because you could be on either side. That's how you get 50-50. But let's focus on this. If this was the intermediate, and this chlorine that attacked, how do you attack the carbocation? From which side? Either side. So if this was the intermediate, you should get both of these. No change here, but then when you attack the carbocation, it should be from either side. So this mechanism should give both, but you don't get both. You only get trans. This tells us that it's not a carbocation intermediate. But we've said that already. By the way, if we attacked over here, then this came in either way. There'd be no change here, but you'd get either up here. And again, we know the cations are not formed. Instead, I don't have this drawn, we know that doesn't happen. Instead, this comes in and does this, right? I'm going to have to draw this over here. And when that back bonds, what's it going to look like? This bond is still forward. Now this is bonded here. Well, how is that bond going to be projected? The answer is actually easy. It's also forward. And your chloronium ion is going to look like this. It has to be forward. Here's the cyclohexane. And this bond is, this chlorine's forward. If it then makes a bond up here by these electrons attacking, it's also got to be forward because it just bonded. It's impossible for this to be this way, and then the new bond it makes coming from the back, that's impossible. These electrons just bonded up here, and so they both are forward. Has to be. This is the intermediate. Then the chlorine comes in, attacks here, and kicks this back off. But importantly, when it attacks here, how does this come in?
Backside.
We're attacking and kicking it off. It comes in only backside. And if you come in backside and kick this off, what do you get here? You get this came in backside. And that's why you get trans. Ultimately, this is opposite of this because it came in backside to this. Backside only. Ultimately, it's the difference between attacking carbocation versus attacking something backside. Terminology here, very top. Since this is the product, we know that the chlorines have added, in terms of stereochemistry, they've added anti, which is the same as opposite. Anti-addition of chlorine across the pi bond. Or you can call it trans. Trans addition of the halogens across the pi bond. That's why we said anti or trans addition of X2 to alkene. Not cis. Okay, let's look at another reaction type. Here we're going to bring in water. If you mix water with your halogen, you're going to get a different product. You're going to get what's called a halohydrin. And it will be trans when that's applicable. Because we'll be doing the same mechanism. Okay? And we need to know why when you get this product, the chlorine is going to be on the N carbon and not here. The reaction is thus regioselective. Mechanism. Let's see, this attacks here, that gets kicked off. Do you want to skip to carbocation intermediate? If you want to, we can just back bond all together. What does that give? Boom, 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 boom. Everybody with me? Or would you rather I draw the carbocation and do it more stepwise, even though it's not? Okay. This is what I don't think you guys can easily get. It's too many arrows. All right? I skipped the NAF, like most books do. Chloronium ion. Here, though, the water attacks. If you got water, it will attack the chloronium ion. Which carbon of the chloronium we're going to attack, left or right? It's the same place we would have made cation if we had formed it. Right? It's on the left. Okay? The water attacks. We come in here and kick off the chlorine, and we end up with boom, 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 boom. And let's draw another methyl. I'll draw the oxygen here. And we have the water now bonded. We cannot just lose an H magically. The H is lost in a next step. Something has to take the H. What can take the H? Well, we did produce Cl minus here. Cl minus does not attack. When you have water, it attacks. The Cl minus can take the H, and if it did, we leave the electrons behind, we can get this product with the oxygen now having two lone pairs. But what else was formed in this reaction? Yes, plus HCl. Do you understand why the oxygen is bonded to this carbon, though? Where did all that take place? Right here. Why did the oxygen bond to this carbon? It was explained on the previous page. And we'll do that 25 more times, but we've already explained why. It's the same place we would have made cation at if we had shown cation. I would actually recommend not doing this arrow because I think it's too confusing unless you guys have it. I would just do the first one and get the cation here, then understand back bonding. And the back bonding leads to here, but guess what? This is not actually formed. We know that. This is just us on the board helping us to understand things. This is called a halohydrin. Sort of like halogen and hydro for water. But you both had halogen and water, a product from there, halohydrin. Common reaction. Please be looking at the stereochemistry. If you have a bromine in water, we're going to get this stereochemical outcome. That is, the bromine in the OH will be trans. Okay? We also need to be looking ahead at what enantiomers mean. It's basically the mirror image. And please also be working problems that are ahead, including these at the bottom. And we'll see how we did with these first thing next time on Friday. that's our time. In lab today, tomorrow, I think we should meet upstairs.